Hello, everyone. So let's dive directly into the presentation, which is about rewriting Pion in Elixir. I know that you've already heard so many WebRTC talks, but I would like to start with a short reminder about WebRTC protocol stacks. So this diagram presents 10 different protocols that WebRTC consists of. Every single protocol is responsible for something different, right? So for example, ICE is used to establish peer-to-peer connection, RTP is used to transmit data as RTP to encrypt this data, and so on and so on. To fully support WebRTC, we of course have to implement all of those protocols. And the most popular WebRTC implementation is libWebRTC. It's used by web browsers, written in C++, and it's maintained by pretty big companies like Google, for example. But the problem with libWebRTC is that it's pretty hard to play with it. It's hard to install it, it's hard to compile it, it's hard to introduce any changes into it. And all of those problems are solved by Pion. So Pion is another WebRTC implementation written in Go. It implements everything from scratch. So every single protocol I showed you on the previous slide is provided as a separate package. It's very fast and popular. And the phenomenon of Pion, I think, is that they made creating your own web applications, or in general applications based on WebRTC, much easier than this was before. They even come with WebRTC for the Curious book, so their own learning resource. And Elixir WebRTC is our attempt to create a similar project, but for the Elixir community. So we don't want to rewrite everything one-to-one from Go to Elixir. Instead, we want to take inspiration and create a similar ecosystem for the Elixir community. We don't want to follow WebRTC path where they even have the same function names in their implementations. But you might ask a question, why Elixir? Have I ever heard about this programming language? And those questions are very good questions because Elixir is not so popular. Comparing to Go, Rust, or C++, is also pretty slow. Functional and dynamically typed, most of us are used to some kind of object-oriented programming, and there already are WebRTC implementations available on the market, so why create another one? Doesn't make a lot of sense, right? I would like to leave those questions for a while and talk about bigger picture, bigger context, some problems that a lot of people face when they jump into the multimedia. So imagine that you want to create a startup, right? You want to, as in the case of every startup, you want to create a prototype pretty fast to show it to the investors. Or you have a company and you don't want to run your meetings, internal meetings on a Google Chrome, Google Meet, because you cannot host it on your own machines. Or you are a student and you want to learn something about audio and video. In general, you want to do something with multimedia, you decide to jump into this world and you immediately feel overwhelmed by so many weird terms, codecs, network protocols, and different RFC documents, overwhelmed by few learning resources, legacy network stuff, or pure user experience. And in general, you have two options. You either try to jump into this world on your own and try to understand what's going on, but this will require a lot of time from you, or you pay some consultancy company to do this multimedia stuff for you. And that's something that we want to change. We want to make multimedia more accessible, easier to jump into. We want to provide you with a good learning tools, good learning resources so that everyone can play with audio and video on their own. During those 3 years of working on multimedia projects in software management, specifically in Membrane, we had a lot of clients, everyone with custom needs, different needs. For example, a client comes and says, I want to have a video conferencing system with recordings. Or another client comes and says, I want to have a video conferencing system, but with the ability to broadcast it to a broader audience. Or another client comes and says, I want to fetch audio and video from my web browser and transmit it to the backend and apply some cool ML stuff on it. The only common thing was that people needed to use the same network or multimedia protocols, but for different purposes, in different configurations, and with custom enhancements. So we created something called Media Engine, officially known as Membrane RTC Engine, and that's a library that allows you to combine different multimedia protocols. So once again, imagine that we want to create a video conferencing system, right? So we take the engine, we take two WebRTC endpoints, plug them into the engine. Those WebRTC endpoints will communicate with web browsers, exchange their media between each other, and that's it. we have very simple video conferencing system. Now let's assume that we want to add recordings. We no problem, we just add the recorder endpoint. Maybe we want to broadcast this to a broader audience, no problem, just replace the recorder with HLS endpoint. Or even better, have both at the same time. Maybe you don't want to use WebRTC at all, no problem, replace WebRTC endpoints with RTSP endpoints. And so on and so on. There are, for example, ML endpoints, or you can create your own custom endpoint by implementing very simple interface. And everything is provided as a library. So speaking of requirements based on our client needs that we observed during those 3 years, almost everyone searches for a customizable solution, written in a high-level programming language so that developers can almost immediately jump into and start prototyping. A solution with built-in fundamental protocol support, intuitive API, good package manager and documentation tool, and pretty wide ecosystem. And it turns out that Elixir is a perfect choice because it's very high-level programming language with an easy-to-understand concurrency model based on message passing and data immutability. So there is no, there are no shared states, there are no mutexes. We have Phoenix for web applications, Livebook and Elixir NX for machine learning, and also Mix and Xdoc tools. Yep, so to sum up, we have 3 abstraction layers. If you want to prototype, just take the engine as building blocks, including our WebRTC implementation, and do your stuff. If you want to deploy, just take Jellyfish, which is based on our RTC engine, and deploy. If you don't want to deploy or prototype, and you just want to have everything, you want to be provided with everything, just take our cloud. So Elixir WebRTC is just a small puzzle of this bigger context, bigger picture. I would even call this some kind of a vision. And we started our work on it about 3 months ago. There are currently 2 people working on this project. And going back to the diagram I showed at the beginning, we were able to implement coTURN and ICE. We also implemented RTP and RTCP parsers and serializers. Now we move to the peer connection, where we are working on DTLS handshake. So that's the current status of the project, and I would like to go through our libraries, namely coTURN and ICE, and talk a little bit about challenges we've met and how we solve them. So let's start with rel, which is a shortcut from relay, and it's our own pure Elixir TURN server. What is a TURN server? Just a short introduction. So the idea of a TURN server is pretty simple. We just want to forward traffic from the one side to the other side. When you start a TURN server, it comes with a listener socket, a client, and a peer. A client creates an allocation, which is another socket. And whatever peer sends to this allocation socket, this data will be forwarded to the client via listener socket. One client can have one allocation, and it can communicate via this allocation with multiple peers. And we can, of course, have multiple clients, but the very important thing is that every single client has to communicate via the same listener socket. So listener socket here is a potential bottleneck. And I said that Elixir is not, at least comparing to Go, Rust, or C++, the fastest language. So we did a couple of benchmarks. We picked 3 different TURN server implementations and checked which is, let's say, the most performant one. So benchmarking scenario is pretty simple. We'll have a client and a peer. Client creates an allocation. Peer starts sending data through this allocation to the client, and then client echo back this data to the peer. The questions are how many such connections we are able to handle, how big bit rates we are able to handle, and what is the impact of datagram payload size on our TURN server performance. Testbed, we have 2 pretty big machines, Big Fish and Big Cow. Both are 32 cores, 64 threads, and they are connected with 10 gigabits per second connection link. A Big Cow handles our TURN server, a Big Fish handles our clients and peers. And the results. So we picked, of course, our own rel TURN server written in Elixir, coTURN, the most popular one, currently available on the market, which is written in C, and a tuner written in Erlang. We started with a phone call-like scenario. So we send 50 kilobits of data per second in one direction. We have 2,000 connections. Datagram payload size is 150 bytes, and the overall bitrate is about 400 megabits per second. The overall bitrate is a sum of total incoming and total outgoing bitrate on our TURN server machine. And rel takes 25% of CPU usage, coTURN 10%, and a tuner written in Erlang, well, we were not able to set up more than 1,000 connections. I think that that's some kind of configuration problem, but that we were not able to easily fix. But I put it here because it crashes in the last scenario, and I would like to talk about this this more. So I would say that the results are pretty good, pretty decent. I'm really satisfied with them. We are just 2.5 times slower than coTURN, which is written in C. But we also ask a question: what happens if we keep the bitrate but increase datagram payload size? So the second scenario is almost identical, but datagram payload size is 1200. And the results are much different. The difference is massive. RHEL takes mostly between 2 and 4% of CPU usage. coTURN a little bit over 1%, and the tuner are out of the category. As you can see, if we keep the bitrate but we decrease the number of datagrams that are sent through the network, we of course save a lot of resources. And the last scenario is a video call like scenario. So we have 1,000 connections. We send 1,500 kilobits per second of data in one direction. So this should be enough to handle HD resolution. And the overall bitrate is over 5 gigabits per second. And in this case, RHEL takes about 45% of CPU usage and coTURN 15%. So we are about 3 times slower. A tuner crashes, but by crash, I don't mean CPU usage. I mean that they are not able to read incoming traffic fast enough so that we notice a packet loss. And speaking of this, that's the initial architecture we started with in RHEL. So we have one listener process that was responsible for reading all incoming traffic and splitting this traffic across allocation processes. The problem is that this architecture doesn't scale well. So we were able to set up about 700 connections using this setup, and then our listener process was not able to read incoming data fast enough. So at this stage, we knew that we need to add more listener processes. Defined architecture is as follows. We use reuse port option for UDP socket. Thanks to this, we can open multiple sockets bound to the same IP address and port, and operating system under the hood performs splits incoming traffic across all of those sockets equally, or at least it tries to do this equally. So we get load balancing out of the box. And with this architecture, we are able to handle at least 3,000 or 4,000 connections over 5 gigabits per second. And we start as many listeners as we have threads in our operating system. So that's also the same what coTURN does. They spawn also as many listener processes, listener sockets as you have threads. And that's also why a tuner crashes, because they spawn only one listener, so they are not able to handle pretty big bitrates. RHEL is publicly available. I said that we want to make multimedia world more accessible, so we created one instance of RHEL and made it available for testing and experiment purposes. So everything you need to do is to execute very simple post request to obtain your password, username, and just copy paste this data into RTC peer connection constructor, and this should work. So that's everything about our TURN server, and the next library we implemented was XICE, which is our pure Elixir ICE implementation. Here I would like to list features that we support right now. So we are compatible both with aggressive and regular nomination. We support role conflict resolution. We support almost all types of candidates, transaction pacing, and keep alive on valid and selected pairs. I know that there are a lot of buzzwords, but for those who are familiar with ICE, now you know what you can expect from our implementation at this stage of the project. And the last library is STAN. So what is STAN protocol? STAN, you can think about STAN as a tool that is used both by a TURN server and ICE. It is, for example, used to obtain your public IP address. So let's imagine we have a client which is in a private network behind some NAT device, and we want to obtain our public IP address. We have two types of messages: binding request, binding response. Client just sends a binding request to the server. Thanks to this, it creates a mapping from private to public IP address, and then server sends a response that contains this public IP address, and that's pretty much it. Those messages, binding request, binding response, are most frequently used in the initial state of ICE when we try to establish a connection. So because of that, we did a couple of benchmarks to see how much time we need to encode and decode those messages. We once again picked 3 different implementations. So we picked our own Elixir WebRTC IORTC, which is written in Python, and Pion written in Go. Pion was, of course, the fastest implementation in every single category. We started with binding request encode, so how much time we need to encode binding requests. In this case, Elixir WebRTC is faster than IORTC. We just need about 1,700 nanoseconds. IORTC about 2,400 nanoseconds. So that's pretty, I think, significant difference. The next benchmark is binding request decode. I don't know what IORTC does in this time, but they need over 2,000 nanoseconds to decode binding requests. Elixir WebRTC takes about 150 nanoseconds and Pion just 9. And binding response encode. And once again, I don't know why IORTC is so slow. I don't think we have a bug in our benchmarks. This code is also publicly available, so everyone can check it out. But the code is very simple. Here, Elixir WebRTC and Pion are the results are pretty similar. The last benchmark was related to new transaction ID. So when you send a binding request, you need to generate transaction ID. When you send the response, you just take the ID from the request. Here, Elixir WebRTC was the slowest implementation. But to sum up, in most cases, in most categories, we outperform Pion. I mean IORTC. So Python implementation. And as long as we outperform Python implementation, I'm satisfied with the results, and I think there is some sense in continuing this project. Yep, and we hope to be able to provide first version of peer connection in January 2024. And I also spoke about Membrane RTC engine, that is a library that allows you to combine different types of multimedia protocols. It's already available. We use it in Jellyfish, but I also think that the current API is not so intuitive. The documentation maybe is not the best. So I hope that we will rewrite it and provide a new API somehow around June 2024. Well, that's it. That's everything from me. If there are any questions, I will be happy to answer them.
All right, and the questions, are there any here? Oh, okay. Maybe I'll start here.
So, great talk.
Thank you.
I have a question about the RTP and SRTP. How is the progress with that? And are there any challenges in implementing those protocols?
So right now we were able to implement RTP parsers and serializers. We are not sure how the abstraction of data flow should look like. So we will probably start with a peer connection. We'll try to make data flowing, and then we'll try to extract something like Pion provides. They provide session bean, maybe not session bean, but RTP session or something like this. So that's how our RTP implementation looks like right now. Regarding SRTP, we'll take the implementation from already existing implementation from Membrane framework, and cryptography and anything related to cryptography will stay in C. So we are not going to rewrite cryptography stuff in pure Elixir. We of course take already existing implementations and wrap them for usage in Elixir.
Thanks.
Yeah,
Great talk. Thanks a lot. Very deep, but still very clear. Noob question. You said you're going to re-implement all the 10 transport protocols. Are you even going to rewrite UDP? That's insane.
Thanks for the question. So here I marked UDP with the gray color because or maybe it's not visible on the presentation, but it's marked with the gray color because we are not going to rewrite it.
All right, any other questions? Okay, thank you very much.
Thank you.